morning, guys. Today we will be doing some mathematical exercise on tensorial operations, and I'd like to give you very basic procedures to start with. So we have a couple of questions here to evaluate expressions to scrutinize and understand very well how the language of tensorial mechanics works. Okay, so for the first exercise or problem, we are asked to convert this explicit or expanded. Okay, so this is the explicit or expanded notation. And we know for a fact that when we have a summation series, we learned from the basic rules that we indeed have a repeated index. Okay, so but before we proceed with that, the usual form of this summation series is written in the form S is equal to the summation from I equals 1 to, say, n of your AI xi. So this is the most compact that we can get out of it. But basing on initial notation, we can simply drop the summation symbol and finally come up with an equation equivalent to this one. Okay, so this very compact, very short form of an equation is actually the perfect representation of this explicit notation. So for the second problem, we're asked to find the meaning of this expression. And we have learned from our basic rule again that there is no such thing as a triple repeated index. Okay, so so the index is repeated twice, or sorry, thrice, and this is a no-no, okay, in continuum mechanics. So there's no such thing as this expression. There's no meaning. In continuum mechanics, if you see this, this could be a special case that you have to treat for simply a specific use, no? But in general, this term here has no meaning. So for the third one, fourth, and fifth, and sixth, we are just asked to simply determine the order of the tensor and how many components are there. When we are referring to components, we simply refer to the vectorial or tensorial quantity, number of quantities that is inserted into the expression. So we say that your scalar function has one component. Okay, your vector has three components. Okay, if your index or range is from 1 to 3, and your matrix has 9 components if the index is I equal to 1 to 3. Of course, the scalar, any value of n or I can actually be use, and it will yield to the same number of components. So this is the meaning of the word component there. So for this particular scenario, we need to expand, okay, in order to get the number of components we have. Or simply use the rule, no? And we know that the rule states that we can contract, okay? So simply by contraction, I and j will collapse and it will yield to a 0 degree, okay? Okay, tensor or a 0 rank tensor, and therefore your number of components is simply 1. So it becomes a scalar in this regard. And so it's true with this one here. We have here an I and a K, and a K simply will collapse and contract, such that again this is a 0 degree order of your tensor. Okay, and this becomes again one component, which is a scalar. And so it's true with this, no? So these are repeated index, and this means simply summations, okay? Then again they will collapse and contract. So this again is a 0 order tensor, equivalent to the number of components equal to 1. Okay? And for the last, we can say that these are all terms or expressions. Okay, so these are single terms. But here we have an equation, and the equality of the left hand to the right hand must be satisfied. In the left hand side we have a single term, in the right hand side we have two terms, but they have to be compatible. Okay, so if we take a look at this will collapse, so your index will be I, and then here your LL also will collapse. This is a summation, and your index will be I. And this also index is I. So the index here are consistent. That's why I call this now a free index, which defines the degree of your tensor, which is 1. Okay, sorry. Okay, so this is a 1 degree tensor. So 3 to the 1 is simply equal to 3 components. Okay? So express the vector in U in a Cartesian coordinate axis using the indicial notation. So this is a vectorial symbol. And this is the component. We have actually 3 components in a vector. Just like what the number 6 problem is all about. This is a vector. Just 3 components. 1, 2, 3. And we are asked to express it in terms of the Cartesian coordinate axis using indicial notation. All we have to do is to place U with a subscript, let's say I, and then equivalent. So we know that a vector must have a magnitude. Okay, it has a magnitude and a component. Okay, so this is a U1 direction. Okay, so magnitude, direction, these are the unit directional vector, plus, okay, U2 plus U3. Okay, of course, to make this complete, you must have a UI. Okay, so this is now the expression of such vector or tensor in the indicial notation, and this is the expansion of such a vector in the inditional format. or in the initial format. Okay, so this is expanded. So we can write a vector in terms of components, or a vector or a tensor in general in terms of a mathematical equation. These are vectorial addition, okay? So we cannot simply add it because there are directional vectors inside the magnitudes, each magnitude, okay? So for number 8, the dot product means a projection of, or taking the component along a direction vector and multiplying it with the other vector. So if I have two vectors involved, let's say I have a vector u here and a vector v here. Okay. So what is my dot product? So this is a special. Dot product is a special operation. Okay. Special multiplication operation. So you are now taking, okay, the component of u vector along the other vector, or along the direction of the other vector, and multiply them together. Okay, so if I want to take the magnitude, I want to take the magnitude of such resulting vector. What's the resulting tensor here? So the result will be scalar with a magnitude equivalent to this times this one, or simply your u times v. Okay, if I have here an angle between them, this is simply cosine of theta. Okay, so this is cosine of the angle between them. Okay, so it's let's make it more accurate. So this is v times u sine of theta. So we are talking here of the resulting magnitude only, in which the direction is no longer should I say important, since the product of such vector will yield to a scalar. Okay, so if you want to do it in a matrix format, this is the operation in terms of vector and matrix. So we have a row multiplied by a column. Okay, so this is a row vector and it's a column vector. So we just multiply u1 v1, u2 v2, u3 v3, and you get the same result with that using simple geometrical interpretation. Okay, so the problem with the dot product is sometimes it is interpreted differently when your row and column vector are interchanged, such that I make a transposition between this v transpose and I place it first here, then I multiply it, so my resulting equation is no longer a scalar. So the result here is another vector. So we will be trying to dig up this particular operation. So if this is a vector operation, this is now what you call a tensor operation. So tensor dot product has a different procedure and meaning compared to a special dot product used in vector operation. Okay, so we will check some of these um, operations later when we need them or encounter them later. Okay, we also have what you call the unit basis vectors represented by the letter E. Of course, there's a caret symbol here. I cannot place a caret symbol in MathCAD. So normally the E there simply gives you an idea that this is a unit-based vector. It is actually a directional vector with a magnitude equivalent to 1. Okay? So what is EI dot to EJ? Okay, so again, this is EI, EJ. So the interpretation of a tensorial dot product in this manner becomes consistent with what? This is an IJ, therefore this is 1 and 1, therefore this becomes delta IJ. Okay? So how do I know that this is delta IJ? Because if I interpret it on the basis of the values of E, okay, directional 1, 2, 3, okay, so this is 1 unit. If I dotted E1, E1, what is the projection of E1 to E1? It's simply equal to 1. Okay? Okay, so if I make use now of a matrix, E1, E1, and then E1, E2, then E1, E3. Okay, so let's make it larger. Okay, so this becomes E1, E1. Okay, that's that. Then E1, E2, E1, E3. Then you have an E2, E1, E2, E2, and E2, E3. And then we have an E3, E1, and E2, E2, and E3, E3. Okay, so E is a unit, 1. Okay, so this is now 1 times 1. So all of this will become 1. And the projection of E1 to E2 is 0 because these are perpendicular. And therefore, these are all 0. So we can go back to the basic Kronecker delta, delta Ij. So if I dotted now EI, EI, so what's the answer here? Okay. So this is a summation series. So it's an E1, E1, 1 times 1, 1 times 1, 1 times 1. So these are 1 plus 1 plus 1. Okay, summation series. So it becomes a scalar equivalent to 3. Okay, so EI, EI is actually equivalent to a delta II, which is also equal to 3. Okay, so take note of this basic operation because this will help you understand and look into the complex operations much more easier if you are very well uh, informed about these basic operations. Okay, what's the cross product? A cross product against a special vectorial operation which is also applicable in tensors, and you are just simply getting the area by means of a determinant. Okay, so if I have here a vector, let's say a vector v and a vector u, so the cross product of this is a vector, okay? A vector crossing a vector u is another vector w, okay? And where's that w vector? The resulting vector is actually a vector perpendicular to the plane on which the two vectors are oriented. Okay, so if this is the plane of the vectors v and u, then this is now perpendicular to this one. And the magnitude, this is now the direction, the magnitude of this vector is actually equal to the area of the parallelogram here. Okay? And this can be done using an area determination using a determinant. Okay, so a determinant is actually represented by an permutation. Okay, so discussed this in the first lecture. So therefore, this EI cross EJ, if I will just look into this definition, is simply equal to epsilon IJ. So I just add any dummy index, let's say K, and make a directional, okay? Okay, a directional unit-based vector to emphasize and to make obvious that this special tensor happens to be a vector. Okay, because I and J, K and K here will simply be consistent, no? Of course, this does not mean it's a summation. Why? Because this is just a description of what? A direction of such epsilon ij. You can use M, L, X. You can use any letter for as long as this must be always consistent. Okay, how do I know that this is ij? Because I have an I there and an I here. So you cannot make this a different index unless you change the index here. So these are what you call free index, okay, in this regard. It's a free index. How many free index do I have on the left side? I have 2. How many free index do I have at the right side? I have 2. So they are consistent. So the order of this equation, okay, the order of this equation is now consistent as far as the left and the right hand side is concerned. Okay, so that's the meaning of a cross product. Applicable for vectors, of course. On the tensors, there are additional rules that you have to follow in order for you not to be confused. In fact, these rules are the source of what you call the language of tensorial mechanics or indicial notations. Okay, so express the indicial notation in this regard. So this is a vectorial notation. So I want to express this, but I know that this is expressed in terms of an indicial notation EI, UI, EI. Okay, I cross it with VI, EI. Okay, so this is my equivalent cross product or vector product. Okay, so this is now the vector product. Sorry class, these are not i's, no, because it will actually be a different vector, so this must be changed into a different index in general, of course. Sometimes the problem will lead you to this being of the same index. Okay, so in general, this is now UIEI cross VJEJ. And if I make this simpler, this is simply a UI, VJ, and then I place my EI cross, okay, EJ. I don't want to use the tensor. I just make use of symbols here because that symbol was used in another rule. Okay, so this is EI cross EJ, but EI cross EJ is simply what? Okay, epsilon I J K. So I now finally have a UI VJ epsilon I J K EK. Okay, so this is now the representation of the vector notation to an initial form. And I just like to add some books and some references using this, but I really don't want to use this. So this is simply equivalent to a component vector of another vector along the direction L. Okay, so this is now what? A U I E I cross V J E J, and then projection means, okay, so you're just crossing it to EL, or dotting it, dot product to EL. So why is it EL? Because this is a simple projection on the unit direction L. Okay, so this is L. If you want to simplify this further into this one, you may do so. Okay, so this is becomes UI Vj epsilon I J K EK, and then you dot it to EL. Okay, so this is how you connect things and make some simplifications of what you want to represent on your uh, manuscript. So thank you very much for listening. Have a nice day, and I'll see you on the next video. Thank you.